Welcome to this explainer, where we're unpacking a really fascinating and honestly highly critical reconstruction of advanced radiobiology from the European Committee on Radiation Risks 2026 textbook. If you work in health physics, toxicology, or environmental regulation, you're already intimately familiar with the prevailing models. But the source material we're looking at today asks us to view the evidence through a completely different lens, arguing that our globally accepted radiation safety model might actually be fundamentally flawed. Let's get right into it.
The text kicks things off by posing this massive, somewhat unsettling question about the very structural integrity of how we measure radiation danger. For over 70 decades now, global radiological protection has leaned heavily on one specific conceptual framework. But the ICRP's text argues that while this framework totally works for external radiation, it structurally falls apart when dealing with chronic internal radionuclide contamination.
To really grasp the critique here, we first have to look at the currently accepted standard, the absorbed dose. Measured in grays, it calculates radiation exposure based on the energy deposited per macroscopic kilogram of tissue. It's the absolute bedrock of modern radiological protection. But according to our source text, it has a glaring blind spot when it comes to internal emitters.
So today, we'll be following the text forensic investigation through 5 key areas. We're starting with the bag of water model, moving into a forensic history, looking at track structure and DNA, exploring the high Z effect, and wrapping up with a totally new radiation paradigm.
Section 1. The bag of water, the flaw in the foundation.
There's a stark difference in how exposure is modeled depending on the source. With external irradiation, those tracks are uniformly distributed throughout the tissue mass. And for that, the text concedes that averaging the dose over a full kilogram is actually a pretty reasonable approximation. But internal irradiation is a totally different story. The conventional model treats complex human tissue as quite literally a homogeneous bag of water. It takes these highly localized internal radioactive strikes and just averages them out across an entire organ. Think about it. If a particle of uranium is inside your body, emitting a localized track of extreme energy, the textbook argues that averaging that energy across your whole organ heavily dilutes the true localized damage. The real physics are happening at the nanometer scale, not the kilogram scale.
Section 2. A forensic history, from discovery to capture. The textbook reconstructs this forensic timeline, suggesting that the bag of water model wasn't exactly a biological triumph, but rather a mathematical convenience. Going back to the 1920s, young women painting luminous clock faces ingested minute amounts of radium-226 and suffered horrific, fatal systemic diseases. Then, fast forward to the Manhattan Project in 1947, and physicist Herbert Parker proposes this mathematical bag of water model to quantify radiation. By 1952, the text asserts that arbitrary quality factors were adopted basically as a political compromise, a way to keep the nuclear industry operating despite those early glaring warnings. Ultimately, it was a model built by physicists and mathematicians, not biologists.
According to the text, whenever workers, like those radium dial painters, suffered systemic diseases from internal particles, institutions would deploy this single legal defense: the dose is too low. Because the energy was being averaged over an entire macroscopic body mass, the calculated absorbed dose appeared vanishingly small. And that defense successfully argued that the physical dose just wasn't high enough to cause harm. But that completely ignored the biological reality of where that energy was actually being deposited.
Section 3. Track structure and DNA, the microscopic reality.
If we're throwing out the bag of water, what should we be looking at? Well, DNA, of course. And the text emphasizes a truly surprising metric here. DNA makes up only 1.15% of a cell's mass. This is a crucial number. It means that if radiation is physically or chemically targeted directly at the DNA, calculating an average dose across the whole cell is grossly underestimating the catastrophic genetic hit. The source points out that for internal exposures, the biologically relevant dose to the DNA is inherently vastly higher than the cell average dose.
You really have to compare the sparse ionizations of low LET radiation, that's linear energy transfer, like external gamma rays, with the reality of internal alpha particles. Alpha particles create incredibly dense, localized tracks of ionization. When an alpha particle strikes, it deposits extreme energy in a microscopic volume. The source explains that this easily causes local, multiply damaged sites. We're talking about complex, clustered double-strand DNA breaks that the body's standard repair pathways simply cannot fix, which very often leads to mutations.
The text argues that we have to completely separate how we think about these two scenarios. External radiation damage is essentially a matter of geometric chance. It's a random strike from the outside. But internal DNA-seeking radionuclides, they act like Trojan horses. Because elements like strontium-90 mimic calcium and actually seek out the phosphate backbone of DNA, or because carbon-14 is literally incorporated right into the DNA structure itself, they have a nearly 100% chance of intercepting their target when they decay.
Section 4. The high Z effect, secondary photoelectron enhancement.
This brings us to a startling chemical mechanism known as the high Z effect. The data reveals a really compelling argument about how different elements react to ambient background radiation based on their atomic number, or Z. Water, with a low Z of about 7.5, produces virtually no tracks. But heavy elements are a totally different story. Uranium, with a Z of 92, absorbs ambient background photons and re-emits them as dense local electron tracks at rates roughly thousands of times higher than water.
A uranium nanoparticle essentially acts as a nanoscale antenna. It takes normal, everyday background radiation and amplifies it into a storm of dense local electron tracks. The source text emphasizes that if this uranium nanoparticle is chemically bound to your DNA, this localized amplification creates absolutely catastrophic damage that a traditional dose calculation completely misses.
To address all these microscopic and chemical realities, the ICRP proposes replacing the bag of water with a framework they call radiochemical genotoxicity. It's a system that finally factors in the actual biology. It accounts for chemical affinity, like uranium-seeking DNA phosphate. It accounts for transmutation, which is when an atom, like carbon-14, decays into nitrogen, literally destroying the molecule it was part of. And it factors in the precise physical proximity of that radioactive bullet to the DNA target.
Section 5. A new radiation paradigm, the biphasic model.
A massive part of this new paradigm is rethinking the dose-response curve itself. The conventional linear no-threshold model assumes risk just goes straight up as dose increases. But the ICRP replaces this with a biphasic curve. The source argues that very low doses actually trigger a sharp peak in cancer risk. You might be wondering why. Well, it's because low doses mutate highly sensitive, actively replicating cells. As the dose increases slightly into the intermediate zone, the risk actually drops. That's because the radiation is now high enough to outright kill those sensitive cells, preventing them from ever becoming cancerous before the risk rises again at high doses. The traditional linear model completely misses this low-dose danger spike.
To apply this biphasic and chemically aware model practically, the textbook outlines the Müller system. It replaces arbitrary quality factors with precise biochemical hazard factors. It also introduces the Müller, named for the geneticist Hermann Joseph Müller, as a brand new unit of genetic dose to properly assess the real risks of internal radionuclide exposure. And broadly speaking, it calls for a legal and ethical rejustification of all nuclear activities based on this updated biological reality.
So the crucial point the source really wants us to walk away with is this. The grade, the absorbed dose, isn't scientifically fake. It is a perfectly valid physical measurement of energy. However, physics alone cannot predict biological harm without biochemistry. Once we factor in where the energy goes, what chemicals are involved, and exactly how the DNA is targeted, the old macroscopic model simply ceases to be a valid predictor of human health.
Which leaves us with a final, rather provocative thought to consider. If the evidence presented in this textbook holds true, the foundational math of our global safety standards is totally mismatched with biological reality. So, how will our legal compensation systems, our environmental safety regulations, and our public health institutions adapt to a nanoscale framework that fundamentally challenges 7 decades of established law? It's a massive, massive question for the future of radiobiology. Thank you for joining me on this explainer, and I highly encourage you to keep questioning the frameworks that shape our world.